In this video, we will discuss the computational efficiency of the simplex method. The simplex method is an algorithm that is iterative in nature. So its computational efficiency is the product of two factors: the computational effort for each iteration and the number of iterations. In section 3.3, we have already discussed the computational requirement of every iteration. One of the most important results that we have seen is that the full Tableau implementation needs big O of mn arithmetic operations per iteration. And the same upper bound also holds for the revised simplex method in the worst case. In order to have a complete picture on the computational efficiency of the simplex method, in this video we're gonna discuss only the number of iterations that the simplex method performs. As always, our focus will be on the worst case, so we will study the number of iterations in the worst case. Let's assume that our simplex method performs no degenerate pivot. Then a trivial upper bound on the number of iterations is given by the number of extreme points of our polyhedron defining the feasible region. However, the number of extreme points can increase exponentially with the number of variables and constraints. On the other hand, from a practical perspective, it has been observed that the simplex method typically takes only big O of m pivot in order to find an optimal solution. However, this typical behavior in practice does not apply to every linear programming problem. In fact, soon we will see a family of problems for which an exponential number of pivots may be required. Our simplex method always moves from one vertex to an adjacent one, and at every step it improves the value of the cost function. Therefore, to construct this family of problems that require an exponential number of pivots, I need to give you a polyhedron that has an exponential number of vertices, together with a path along the edges of the polyhedron that visits an exponential number of vertices. Actually, in the polyhedron that we will now see, this path visits all the vertices of the polyhedron. We will also see that in this path, when we move from one vertex to the next, the cost always decreases. Finally, we will see that there exists a pivoting rule that traces exactly this path. Since the path is of exponential length, then also the number of pivots will need to be exponential. In order to describe such a polyhedron, we start from the unit cube in Rn. The unit cube already has many of the characteristics that we want in our polyhedron, but not really all of them. So later on, in few slides, we will somewhat slightly modify such a unit cube. But for now, let's just focus on the unit cube in Rn, which is defined by the constraints xi between 0 and 1 for every I. It's then trivial to see that the unit cube has 2 to the n vertices, and these are all the binary vectors. The next thing that I want to show you is that there exists a path along the edges of the cube which visits all the vertices. This path will be called a spanning path. To see how a spanning path can be constructed in any dimension, we will now see a recursive argument. We start in dimension 2. In dimension 2, the unit cube is this square over here. And the spanning path is the one that starts from this vertex, goes to this one, then moves to this one here, and finally goes to this vertex. Of course, there are many other spanning paths, but we only need to show that there exists one. Now we're going to use this spanning path that we call P2 to form a spanning path P3 in dimension 3. In this picture here, you can see our unit cube in dimension 3. The way we're gonna construct our spanning path P3 is very simple. We look at our new component x3 and we consider separately the face of our polyhedron defined by x3 equal to 0, that is this square down here, and the face of our cube defined by x3 equal to 1, which is this square over here. In this way, we have obtained two two-dimensional cubes. Let's start by looking at the one at x3 equal to 0. Naturally, we can use our old spanning path P2. So we start from this vertex, go here, and then finally go here. At this point, what we want to do is to go to our second two-dimensional unit cube. And so we just move up by changing the value of x3 from 0 to 1. Now we can easily finish off our spanning path P3 by following the path P2 in the reverse order on this upper two-dimensional cube. Therefore, from this vertex we go now to this one, then to this one, and finally to this one. Clearly, this is a spanning path in our three-dimensional cube. Our construction now can be generalized to any dimension, using the same type of inductive argument. So essentially, you can use this argument to show that the n-dimensional cube has a spanning path Pn. Great, so we have a polyhedron with an exponential number of vertices, and we also have a path along the edges of the polyhedron that visits all the vertices. The next thing to do is to find an objective function such that the cost along this path always strictly decreases. Unfortunately, we're not really able to do that. The closest thing we can do is to introduce the cost function minus xn. With this cost function, it's true that the cost always decreases along our spanning path, however, it does not decrease strictly. In fact, we will have that half of the vertices have 0 cost and the other half have cost minus 1. This is why we now need to slightly modify our unit cube. We will see that with a little perturbation of the unit cube, we will also be able to find a cost function that strictly decreases along a similar spanning path. Algebraically, our perturbed cube is defined by this system. So we have x1 between epsilon and 1, and then xi between epsilon times xi minus 1 and 1 minus epsilon times xi minus 1, for every I that ranges from 2 to n. In this system, epsilon is any number in the open interval 0, 1/2. For simplicity, you should think of epsilon as being very close to 0. To gain an intuition on this system of linear inequalities, we should actually set epsilon to be equal to 0 for a moment. If you do so, you immediately see that we obtain exactly our old unit cube. In fact, the epsilon here becomes 0, this becomes 0, and this becomes 0, so then we obtain xi between 0 and 1 for every I. So it's clear that by making the epsilon positive but very small, we will obtain somewhat a perturbation of the unit cube. Still, we don't really have a geometric intuition of what's going on, and so to understand a little bit better what's going on, let's visualize this perturbed cube in dimension 2. In dimension 2, we only have 4 inequalities to draw. In the picture down here, I have in black our old unit cube. So this is the polyhedron given by x1 and x2 between 0 and 1. Now we have to draw the 4 inequalities corresponding to our perturbed cube. Well, one of the inequalities is easy, because it is x1 less than or equal to 1. So this is the vertical inequality over here that also used to belong to the original cube. Then we have the inequality x1 greater than or equal to epsilon. This inequality is also a vertical inequality, and it's just a translation of the old inequality x1 greater than or equal to 0. It's only moved slightly to the right. Next, we need to draw xi between epsilon xi minus 1 and 1 minus epsilon times xi minus 1. If you draw these two inequalities, you will obtain these two inequalities over here that are almost horizontal. Actually, their slope depends on epsilon. In fact, the line below passes through the origin and the point 1 epsilon, while the line corresponding to the inequality above passes through the point 0, 1 and 1, 1 minus epsilon. So now our perturbed cube is the set of points contained in this inner region of the picture over here. It definitely looks like a perturbed cube, and you can see that the closer epsilon is to 0, the closer this perturbed cube is to the original unit cube. It's also clear from the picture why we're considering this perturbed cube. In fact, now there exists a spanning path along which the cost function strictly decreases along it. The spanning path we're talking about is the one that starts in this vertex, moves to this one, then to this one, and finally to this one. In fact, we're still using the same objective function minus xn, which in this case is minus x2, and since along this path x2 strictly increases, then the objective function strictly decreases. Now there's only one thing left to do. We need to find a pivoting rule that moves exactly along this spanning path. If we do so, our simplex method will require 2 to the n minus 1 pivot. And this is because the number of vertices is 2 to the n, and so the length of the spanning path is also 2 to the n. Of course, you can also try to visualize the perturbed cube in dimension 3. Here you have a picture. However, it is admittedly a bit complicated, so don't worry if you're not able to fully visualize this in dimension 3. At this point, we're ready to summarize our discussion in the next theorem. Consider the linear programming problem of minimizing minus xn subject to the constraints that define our perturbed cube. Then, A. The feasible set has 2 to the n vertices. B. The vertices can be ordered so that each one is adjacent to and has lower cost than the previous one. And finally, C. There exists a pivoting rule under which the simplex method requires 2 to the n minus 1 changes of basis before it terminates. We have already seen a sketch of the proof of points A and B, and I encourage you to write down a complete proof of these 2 points. On the other hand, we didn't discuss how to prove point C at all. If you're interested in seeing this proof, I refer you to exercise 3.32 in the textbook. The pivoting rule discussed in Theorem 3.5 essentially goes through the spanning path in the perturbed cube, and so it requires an exponential number of pivots. However, notice that the optimal vertex is in fact adjacent to the starting vertex, and this happens in the perturbed cube as well. So while the pivoting rule that we discussed takes an exponential number of pivots, with a completely different pivoting rule, we could have gone to the optimal solution in just one pivot. In fact, the complexity of the simplex algorithm really boils down to the pivoting rule that is used. So a natural question is whether there exists a pivoting rule that always achieves a polynomial number of iterations. Or, vice versa, is it true that for every pivoting rule there are examples where the simplex method takes an exponential number of iterations? Unfortunately, for several of the most popular pivoting rules, we have examples where they take an exponential number of iterations. However, there could always be a new pivoting rule, maybe that nobody introduced yet, that will always result in a polynomial number of iterations. And this is one of the most important open problems in the theory of linear programming. In order to make progress in answering this open question, researchers study the diameter of a polyhedron. And this is what we're gonna discuss next. What I want to do now is to define what is the diameter of a polyhedron. As soon as we define it, we will immediately understand that it's closely connected with the number of iterations performed by the simplex method. Let's say that from any vertex of our polyhedron, we're only allowed to jump to a vertex that is adjacent. For example, in this picture, if this is our vertex, we're allowed to jump either here or here. Then we can define the distance between two vertices x and y. This distance is denoted by dxy, and it is the minimum number of jumps required to reach y starting from x. For example, if this is our vertex x and this is our vertex y, then the distance will be 2, because to go from x to y we only need 2 jumps, namely, this is the first jump and then the second jump. Of course, we could have taken a different path, namely we could have gone all the way down below from x to y, but this would have required 1, 2, 3, 4, 5, 6 jumps, and the minimum between 2 and 6 is equal to 2, so the distance between x and y is equal to 2. If we look at the polyhedron on the right, which is unbounded, then for every pair of vertices x and y, there really is only one choice on the path that we can take from x to y. So for example, if this one is x and this one is y, then the distance is 1, 2, 3, and 4. Now that we've understood what is the distance between two vertices, we can define the diameter of a polyhedron. This is denoted by d of p, and it is the maximum of all the distances for every pair xy of vertices. Let's go back again to our example on the left. We saw that the distance between this x and this y is 2, but this is definitely not the maximum. For example, if this one is x and this one is y, then you can easily see that the distance between x and y is equal to 4. Since this polytope has dimension 2 and has exactly 8 edges, it is simple to show that its diameter is equal to 4. More generally, you can show that for a two-dimensional polytope defined by m linear inequalities, then the diameter of P is less than or equal to the floor of m divided by 2. I recommend that you write down a proof of this fact, and note that the fact that we have a less than or equal to here instead of an equality is because some of the inequality constraints could be redundant. Similarly, if our two-dimensional polyhedron is unbounded, then you can show a weaker bound, namely that the diameter of P is at most m minus 2. Now that we've understood the concept of the diameter of a polyhedron, let's see how it connects to the simplex method. Let's say that our polyhedron P, representing the feasible region in our linear programming problem, has diameter equal to a number d. This means that there exist two vertices x and y of our polyhedron, such that the distance between x and y is equal to d. Now let's say that our simplex method is initialized at the vector x and y is the unique optimal solution. Then, no matter which pivoting rule you choose, at least these steps will be required. This is because the simplex method with any pivoting rule will trace a path from x to y along the edges of the polyhedron, and this path must have length larger or equal to the distance between x and y, which is equal to d. Our next task is to look at how the diameter can grow in terms of our two parameters n and m. So, for any pair n and m, we look at the polyhedron which has the largest diameter among all the polyhedra in Rn defined by m constraints. So formally, we define delta and m to be the maximum of the diameter of P over all polyhedra in Rn that are represented with m linear inequality constraints. For example, we have said that if n is equal to 2, then the diameter of P is at most the floor of m divided by 2 if P is bounded, and it is at most m minus 2 if P is unbounded. Now, both in the first case and in the second case, there exists a polytope or a polyhedron that achieves this bound, and the worst among the two bounds is m minus 2. Therefore, this shows that delta 2m is equal to m minus 2. Now that we've defined delta, we can easily relate this concept with the number of steps taken by the simplex method. In fact, if delta nm increases exponentially with n and m, then there exists example for which the simplex method will take an exponential number of steps no matter which pivoting rule is used. So if there exists a pivoting rule which always takes a polynomial number of steps, then delta nm must only grow as a polynomial with respect to n and m. In research, every time you want to prove some statement, it's a good idea to first prove a simpler statement, which is a statement weaker than the original one because it's implied by it. Therefore, if you want to show that there exists a polynomial pivoting rule, you should first show that delta nm is upper bounded by a polynomial in n and m. One of the most well-known conjectures in discrete geometry is that delta nm is in fact upper bounded by a polynomial function of n and m. In fact, the Hirsch conjecture, stated in 1957, says that delta nm is upper bounded by m minus n. So not only this is a polynomial function, this is indeed a linear function with very small coefficients. Many researchers have worked on the Hirsch conjecture for many years. And it's only recently that we know that the Hirsch conjecture is actually false. Klee and Wolcap already showed in 1967 that the conjecture is false. So this result was shown only 10 years after the conjecture was stated. However, the counterexample that they obtained uses unbounded polyhedra. So then after this counterexample, researchers still wondered if the Hirsch conjecture is true for bounded polyhedra. Finally, in 2010, Santos showed that the Hirsch conjecture is false also if we consider only polytopes. The main reason we discuss the Hirsch conjecture really is its historical relevance. However, the fact that the Hirsch conjecture is false doesn't really tell us much. In fact, it only tells us that there are polyhedra with diameter larger than m minus n. But m minus n is a very specific polynomial function, and in our previous discussion we said how we really are interested in understanding if delta can be upper bounded by any polynomial. This leads to the weaker polynomial Hirsch conjecture. The polynomial Hirsch conjecture states that delta nm is bounded above by a polynomial of n and m. So it doesn't specify which polynomial, any one would work. The polynomial Hirsch conjecture is still open and is one of the most important open problems in discrete geometry. Not only this conjecture is still open, many researchers also believe that we're really far from establishing if it's true or false. So there are two cases. Either the polynomial Hirsch conjecture is true or it is false. Let's say for a moment that it is true. Then this still doesn't mean that there exists a pivoting rule that takes only a polynomial number of steps. But it gives us hope that one actually might exist. On the other hand, if the polynomial Hirsch conjecture is false, then this immediately implies that no such a pivoting rule can exist. So we don't know whether delta is upper bounded by a polynomial in m and n. However, we do have some upper bounds. In particular, one of the best known bounds is m to the power of 1 plus log n, which you can also write as 2n to the power of log m. This bound does not answer the polynomial Hirsch conjecture because it's not polynomial. In fact, in the exponents, we don't have just a constant, but we have a function of m or n. This concludes our discussion on the worst-case behavior of the simplex method. Once again, throughout the course, we essentially always look at the worst-case behavior. On the other hand, now I want to tell you a little bit about the average case behavior of the simplex method. The average case behavior of the simplex method is extremely interesting. In fact, even if every pivoting rule requires an exponential number of iterations, in the worst case, this worst case scenario might happen extremely rarely. So from a practical perspective, you might be more interested in understanding the typical behavior of the simplex method. And in this case, you want to understand the average case rather than the worst case. Computational experiments indicate that on average big O of n iterations seem to suffice. Note that this upper bound big O of n first doesn't even depend on m. Secondly, it's a polynomial in n and it's actually just a linear function in n. So not only this number of iteration is polynomial, but it's a very small polynomial. This average upper bound has also been shown in some sense using a probabilistic analysis. Essentially, the smooth analysis of the simplex method proves that instances that require an exponential number of iterations are very non-dense in the set of all the possible instances. And this is because a very small random perturbation of the coefficients of a linear programming problem give rise to just a polynomial number of iterations in expectation. Now, these are very deep results, and I'm not gonna go into any detail, really, in discussing them. What I want to discuss, however, is the main difficulty in studying this average behavior of the simplex method. And its main difficulty lies in defining the term average. In fact, in order to define average, first you need to define a probability distribution over the set of all the problems. Then you need to take the mathematical expectation on the number of iterations required by the algorithm. One of the key difficulties here is that there is no natural probability distribution over the set of linear programming problems. This means that several researchers came up with different probability distributions and obtained average case behavior results based on those probability distributions. While these results are extremely interesting, it is still unclear which probability distribution makes more sense to consider. In this last slide, I want to briefly discuss one of these results, just to give you an idea of how results of this type look like. Let's say that we're given a bunch of vectors. These are our vectors C, A1, and AM, and these are all vectors in Rn. Let's also say that we're given scalars b1 until bm. As you can imagine, C stands for our objective function, A1 until AM stand for the left-hand sides of our constraints, and the scalars b1 until bm stand for the right-hand sides. All this data is given to us, so there's no probability distribution over it. So where does the probability lie in this study? The idea is that for every constraint, we introduce either the constraint less than or equal to with the given data, or greater than or equal to with the same data. And we introduce either constraint with equal probability. This results in a total number of 2 to the m possible linear programming problem. Now the problem here is that many of these linear programming problems will be infeasible. So let's denote by L the number of these linear programming problems that are actually feasible. Clearly, it only makes sense to study the behavior of the simplex method on the feasible problems. Hajmovic, in 1983, showed that using a very special pivoting rule, the simplex method requires only n half iterations on the average case over these L feasible problems. And this number of iterations, n half, agrees with the observed behavior. And with this result, we conclude our video about the computational complexity of the simplex method.